Good evening. My name is Frank Willis. I'm a graduate PhD student at the University of Florida. I'm presenting EEL 6825 course project. That's a pattern recognition course, and the topic of discussion will be the hybrid Bayesian 2D, 3D target tracking using feature extraction. This is my first presentation on YouTube, so please bear with me. Statement of purpose. The intention of this research project was to show how a single target moving in 3 dimensions can be tracked with an extended common filter. Also to show how a common filter can be used instead of the extended common filter in cases where you lose data is corrupted, invalid for sensor measurements. An example would be the loss of GPS altitude. It could just as soon be any other GPS parameter that the constellation provides, but for purposes of this paper is altitude. Another purpose discussion point is use of the Bayesian multiple hypothesis tracking when linear Gaussian assumptions break down. And finally, to show how the use of using the rank of a measurement matrix helps you decide whether you can use the common combination of the common filter and the extended common filter. In parens that says SHT, which is single hypothesis tracking, or you can use a combination of the common filter and Bayesian multiple hypothesis tracking. And I do want to make a statement that the type of tracking we're discussing today only takes one target into account, so no multiple target scenarios. The list of topics covered, obviously Bayes' theorem, Bayesian multiple hypothesis tracking, linear and nonlinear, pretty in-depth review of the common filter, correlation and covariance using the power spectral density and its relationship to autocorrelation, and also discrete and continuous time common filtering. Bayes' theorem, for the purposes of this research paper, especially in this pattern recognition course, we're going to use the term Bayes decision theory. What that is a fundamental statistical approach to the problem of pattern classification. And we'll discuss what that means later on. Key elements to a Bayes decision theory is to define a state of nature. A state of nature describes the state of an entity at a particular point in time. An example of this would be tracking, an aerospace object, which is what this research project slash paper is basically doing. And another question is, what is a state of nature? Now, when tracking an object, you can either find it or not find it. So we call that a detection or a not detection, which basically means it doesn't pass the criteria for declaring a target as valid. What if you don't know the state of nature? Then you have to define it. If you are required to make a decision at some time prior to actual observation, we call that a priori. It's logical to make a decision based on the probability of detection. If it's more likely that the target's detected, I have a note, it's less likely that it won't be detected, so you can declare a track. Using the conditional logic, probability of detection is greater than 1 minus the probability of detection. Conversely, if it's less likely that a target will be detected, it's more likely that it won't be detected. You don't declare a track, and you don't establish a track file and have track updates and the things that go along with establishing and maintaining a track file. A typical probability of detection for what this project models, which is a surface search radar system or even secondary surveillance radar systems such as IFF, identification friend or foe, would be about 95%. There's a technique called sliding window that uses a binomial distribution. If you recall, that's a K out of N distribution, discrete probability distribution. PDF must meet the requirement to be more likely. Continuing with this example, if you can measure a target's position, you can basically put the target position data in a state vector x with x, y, and z coordinate of the target in whatever coordinate system you wish to define it in, northeast down, earth-centered, earth-fixed, and so on. The class conditional density can be defined as the probability of position x, which means all of the data items in x, which would be x, y, and z coordinates for a specific target, given that that's target detected, and the probability of position x given that you don't detect the target. So what that basically says is if you don't detect the target, where is the target really in terms of spatial coordinates? The initial state of a target's position x, x naught, can be sampled from a Gaussian distribution with mean and standard deviation. I have a note that the mu naught is the best initial estimate of the state. Population mean, probably more accurately in terms of modeling this, it should be the statistical or data mean, not the population mean or sample mean. P sub naught is the error covariance matrix, and it has to be initialized, so that'll be discussed later on. The condition is whether or not the target is detected, and that decision, of course, is a binary decision, with true being logical 1 and false being logical 0, or at least that's a convention that I've chosen for this example and for the research paper. Equations 1 and 2 define the likelihood functions of a target being detected or not detected given the position or state x of the target. We just saw those equations on the previous slide. Knowledge of both the prior probabilities coupled with these likelihood functions allow posterior probability to be computed for each state of nature. State of nature in this case being a target's detected or it's not detected. There are probabilities associated with that. The posterior probability we're calculating is the probability of target state x given the state that a target is either detected or not detected. And just to note that the detection threshold is a k out of n criterion. As I mentioned previously, a binomial distribution, at least from my knowledge of secondary surveillance radar systems, and perhaps other systems work that way as well. You'll see equations 3 or 4 are computations of the posterior probability. 4 is the integral form. The form 4 says the probability of state at time t given the probability of state x at the previous time t minus 1 is the integral sum of the probability of the previous state at time t minus 1, which is the previous time, given the range of target z naught at the previous state. And the process noise u at time t and the measurement noise. So what that means is the integration includes these parameters for the process noise and measurement noise. And that is the basis for discrete time common filtering, which we'll see later. The question I have here is there a summation over the right and left hand side of the integral? No. If you remove in equation 3, if you remove the p of x denominator from the right hand side of equation 3, you have the cumulative density function to compute that posterior probability. Also, equation 3 can be interpreted as a probability of detecting a target given the k out of n criterion we just discussed, multiplied by the probability of state and given the probability. An example of this would be a 95% what's called circular error probability. That means there's a 95% chance of finding a target in a circular area defined by a radius of r. I have a bullet that says the probability of this state of nature, omega sub j given x, is computed using Bayes' rule, which is also known as Bayes' formula. So based on our previous discussions, what we're computing is equation 3 from the previous slide, and Bayes' formula is given by the probability of A given B equals the probability of B given A times the probability of A, that product divided by the probability of B. That's set theory notation. For the purposes of this discussion, we'll say is probability state of nature omega sub j given state x is the probability of state x given the state of nature omega sub j. Reminder, state of nature being a target's detected or not detected, times the probability of state of nature omega sub j with the product divided by the probability of a state x. And again, we saw that in equation 3 on the previous slide. Next bullet states, note that the measurement noise mu in equation 4, which is the integral form of the posterior probability, is equivalent to the error covariance matrix, P sub naught that we defined. It doesn't look like it's equation 3, but it is a previous equation. We did discuss it, so I'll note that as an error and move on. And that the probability of the state given omega sub j in the previous equation that we saw, which is either the integral form or the discrete form based on Bayes' rule, is equivalent to the probability of the previous state, which is P of x minus 1 given z naught from time 0 to time t minus 1. X minus 1 is typically referred to as the previous state, and we're going to do that. Excuse me, I should have said z of naught. The initial target position is also from the previous state. And then you see the formula for that in equation 6. Z sub t represents the measured range to target at some time t. It's helpful to think of that as the Mahalanobis distance, which you may recall is the root mean squared or square root of the measured minus actual ranges squared for coordinates x, y, and z, again in any coordinate system that you choose to use. E given the state at time t, that's capital X sub t, given the previous state at time x sub t minus 1. Again, the state vector, we'll say, includes a coordinate x, y, and z for each target. That function is the evidence of a state x at a specific time, or evidence that a target exists at a defined coordinate x, y, and z for that particular target. And you'll see in equation 7 it's the integral sum of all posterior probabilities of all states. The evidence is also called the a posteriori probability or the posterior probability. The posterior probability can also be represented with the following discrete and continuous time forms. Equation 8 is a discrete form, and equation 9 is the continuous time form. And I see that actually on the presentation that's missing, so I'll note that as an error and update it for the presentation when it goes on YouTube. Bayesian multiple hypothesis tracking, MHT obviously means multiple hypothesis tracking. This is a technique that focuses on the measurements rather than the individual targets themselves, specifically hypotheses you want to make about the measurements. An algorithm basically initializes the assignment of a cluster to each target, and a cluster can contain multiple approximate targets in space according to any dimension system you want to use. And we're looking at x, y, and z coordinates, so multiple targets that are approximate to each other. This would be similar to something that you might see in a collision avoidance algorithm where you look for a time the closest approach. That could be a possible application of this type of target assignment scheme with clustering. During the execution of the Bayesian multiple hypothesis tracking algorithm, there are 4 basic steps. Clustering, you take a new measurement associated with a cluster. If it falls within the validation of any region of any target within the cluster. So you measure some data with your sensor. You're going to associate it with a cluster. I think the previous example I use is a circle radius r that there's a 95% chance that a target would fall within that circle, the circular error probability. Hypothesis generation, new hypotheses are generated for the measurements associated with each cluster. The probability of each hypothesis is calculated. I mentioned the 95% CP. That would be an example of one of those. Your target estimates are updated. Then you reduce by combining or eliminating hypotheses, and you simplify the hypothesis matrix and targets that are uniquely associated. In other words, you can't put them in a cluster. They're not proximate to any other targets. They're not targets of interest. They're outside your surveillance region. They would be removed from the hypothesis matrix. We're going to go over some standard types of target tracking. Basically, there are 2, linear Gaussian and the nonlinear multiple hypothesis tracking. We'll begin with the linear Gaussian type. Prior target processes, that's the state of x sub j at a certain time for times greater than or equal to 0. So the target's probably in motion for any number of targets 1 to capital U, where capital U represents the number of targets. I mentioned for purposes of this research paper that subscript j would just be 1 because we're looking at tracking an individual target, not multiple targets. L-dimensional Gaussian distributions at each time t is greater than or equal to 0. Motion processes for each target, they're governed by an independent linear stochastic differential equation. If x sub j at a specific time is Gaussian, the distribution of that state at some future time, t plus delta t, is updated for motion between that time, and the time plus some delta is also Gaussian. So basically the motion process for each target is a Gaussian process. The observations are linear functions of the target state with Gaussian errors. And those are the operational assumptions we'll use for this. I want to make a comment about the L-dimensional Gaussian distributions at each time excuse me, t is greater than or equal to 0. A Gaussian distribution could be, I mentioned the Mahalanobis distance, any of our state parameters. Those individual parameters can each have a probability distribution and hence a number of dimensions. So that's where you get your L-dimensional Gaussian distributions. Another way to think of is we'll discuss Gaussian mixture, that each target can have its own distribution for where the target's located at a certain point at a certain time. To continue at a certain time t, we'll make a hypothesis that associates a set of contacts, i.e. target reports with each target. Using these contacts, we state estimates constructed with a common filter. We're going to update these state variables x, y, and z tabular coordinates with the common filter. The Gaussian densities that result are the state estimates for each target. If a target has no contact assigned to it under the data association hypothesis, it's not detected. We discussed that earlier. It's not part of your state space. Under hypothesis, the joint target state distribution is the product of independent Gaussian distributions. With that being said, we've covered linear Gaussian tracking, now nonlinear multiple hypothesis tracking. There are cases where you can't use linear Gaussian assumptions to model a target tracking problem. What we'll do in these cases is define our state space that contains our targets with their individual coordinates or state vectors. 3 dimensions with R cells in range, B in bearing, and V in velocity. You're basically going to multiply range times bearing. Velocity with this simple model is a vector 1, -1, 0, and 1. Basically, that's decision is whether you decelerate -1, stand still 0, or accelerate 1. So that you're either had a unit velocity standing still or negative unit velocity. Thus, have no here, the state space S has 3 RB states. That's actually an error. It should be, it's R times B. Let's see, that's correct. S has 3 times RB states. When you talk about joint Markov state space, which is Markov on the state space S, you square that, and that's going to get the total value of your state space. In other words, where you can assign targets at a particular point in time according to their range, bearing, and velocity. The multiple hypothesis tracker assumes that the initial probability distribution on the joint state space at time t equals 0, it's uniform over these states in the target state space S. At each time step, the tracker assumes that each target changes course with the probability of one of the other 2 velocities I mentioned. It's unit velocity with the vector -1, 0, and 1 in equation 10 of the previous slide. Each one of those states has a probability, and I believe, although it's not noted on here, I believe the deceleration -1 case and the acceleration +1 case are equally likely, so that would be uniform distribution. And then the state of not moving at all would be 0, and that would be, you could also consider that under a uniform distribution, or you could just look at the acceleration, deceleration. But the point is that vector is governed by a probability distribution that tells how likely you are to move in one of the variables in those states. If a change takes place, new velocity is chosen from these 2 with equal probability. So it's conditional. That's what I was forgetting. The new velocity would be the -1 or +1 unit velocity. That's if a change takes place. If it doesn't take place, it's 0, and you're not updating any tracks. So the target then takes a unit step at velocity. Between the 2 targets, course changes are independent. So one target moving has no influence on the other target moving. Obviously, you could model those sort of factors based on how close the targets are, but that's not what this does. This isn't a collision avoidance type system, so we're not doing that here. The time step is selected, so the target with unit velocity will 1 will move into 1 cell in a time step, and I mentioned the number of individual cells should be this 3 RB states, or actually it would be, yes, 3 times R times B, and the 3 you could put a variable in there, call that V for velocity, and give it a vector of -1, 0, and 1, same difference. The boundaries are elastic, such that if a target hits the boundaries, velocities change in sign. You define a rectangular state space S, which is in 2 dimensions, and when if a target accelerates and hits the edge of the boundary, the velocities change in sign, so you automatically have to choose choose the -1 state, at least for that particular time update. There are use sensors, one in each cell. At the kth time step, sensor A observes a scalar signal intensity. Then you have an observation at the time step, which is comprised of this vector, theta sub t, from 1 to the number of sensors. When a target radiates, it produces a signal eta sub j that decays with range, according to equation 12. It's an approximation to the radar range equation, which I won't discuss here, but this model uses this approximation, and so we'll go with that approximation. And in equation 12, we're also going to say k equals 1 because we're only looking at one target. K equals 2, 3, and 4. Obviously B for multiple targets. That's for the purposes of this research paper. For purposes of discussing this example, the source literature assumed that the number of targets is 2. And again, to clarify, the number of targets is 2 for purposes of illustration, but the project report tracks only a single target with the surface search radar application. So again, the example is with 2 targets. The actual application that will be discussed later is with a single target, or STT, single target tracking. Nonlinear multiple hypothesis target tracking will continue on that track. If a target's a certain number of cells from a sensor and is radiating, the sensor sees a mean signal amplitude, and of course the signal does not depend on the velocity of the target. We know in reality that's not true, but for simple modeling purposes, this will do. For any arbitrary time t, state x of j gives cap state x sub j at some time for j equals 1 to n equals 2. That's 2 targets. We're talking about a state vector again, which is we're taking the state vector information from a sampling from a distribution, which is the cap x. We also have range a comma b in parentheses distance from sensor A to state B, where b equals x. So it's distance from a sensor A to a state X. So between state updates, what's the distance from the sensor to the target? And again, we're going to letting k equal 1. Mu sub j, given the two parameters in equation 15. J equals 1 to n, where n equals 2. Again, k equals 1 because we're just talking about a single target, which I think we actually account for by saying n equals 2, but the k equals 1 is just a simplifying assumption, no more, no less. I apologize for that mistake in that point. The average signal strength received by sensor A is the mean of each, I said B1 and B2, for mean of 2 different targets. If target 1 is emitting and target 2 is emitting, that goes back to equation 15. Well, signal strength seen at individual sensor is specific to that sensor. There's no corruption, no signal overlaps. So we assume that in free space the sensor can receive all the information that's signal. Again, that's a simplifying assumption, not true typically in reality. At an instantaneous time t, or we could say dt, only one of the 2 sensors emit. At time t, we can add a noise for each sensor to the signal received at the sensor at that time, and that's normally distributed with a mean of 0 and variance sigma squared. That's typically called white noise. The noise in the received signal is independent between individual sensors over all time. The observed signal theta sub t for sensor A can be written according to equation 19, and we'll see how that logic plays out, where the white noise is modeled in a common filter. And in this case, the mean between x1 of t and x2 of t would actually describe the state, the mean of the state, or at mean location. The noise in equation 18 is measurement noise, which we described in equation 4 in a previous slide. As I mentioned, we're going to see the use of this later in the common and extended common filters. And I mentioned the assumption independent across sensors. That means no noise is caused by destructive interference due to overlapping signals. Each signal is perfectly received at a maximum threshold level. In other words, the sensor receives the full power of the signal, and the sensors are not close enough to divide the return energy of the signal. So again, more simplifying assumptions as we've seen on multiple occasions throughout this presentation so far. Important assumptions about multiple hypothesis tracking. A scan at time t consists of a vector measurement. We'll say position measurement. That position measurement is generated by one of two targets. Again, this example uses two targets, and there are no false alarms. The tracker knows that only one target radiates at a time. It's not going to be smart enough to know which one. It's equally likely that either target could be radiating, so the radiating target is independent of time. This example fits the assumptions required for independence. So at each individual time, there's only one contact that has a certain measurement, and that measurement will contain measurement of coordinates. In terms of position, again, there are no false contacts. I have a note that one contact per measurement fits the assumptions made on previous slides. No false contacts. That's in a statistical sense, that's a type 1 error or error of the first kind, which would be incorrectly rejecting a true null hypothesis. A type 2 error or an error of the second kind is failure to reject a false null hypothesis. So when we basically say there are no false alarms, we're saying there are no type 2 errors. We have something next called the scan likelihood function, and we denote that by a pair of scan association hypotheses such that we have these two functions, gamma sub t for target 1, gamma sub t for target 2. And the scan association likelihood function is given in equation 22, which I won't bother to go over except to say, if we look at equation 22, you can see the form of a Gaussian PDF. That's summed over multiple, it's the product of multiple Gaussian PDFs times a factor of 1/2, which again we mentioned is two targets equally likely to find either target over the product of multiple Gaussian distributions based on the number of targets. So in other words, a scan association likelihood function is half the product of the sensor's Gaussian PDFs. Just for a quick review of the Gaussian probability density function, any non-negative function which integrates to 1 or unit total area suitable for use is a probability density function, Gaussian. The most general Gaussian PDF is given by shifts of the normalized Gaussian, which is shown at the bottom of this slide. And Gaussian, of course, has two parameters, the mean and the variance of distribution, which we've already seen in previous slides. The scan likelihood function, L sub t, satisfies the definition of conditional independence. We're going to develop our measured ranges. The example I used was Mulholland-Nobis distances by a scan or an observation likelihood function of the form in equation 22. Of course, equation 22 is a scan association likelihood function, which contains the Gaussian PDF, which I just described. Now, the motion models of targets are independent, so the model is of an independent multiple hypothesis tracker mode. For the common filter, we'll do a quick review. The common filter estimates the state of a plant given a set of known inputs and a set of measurements. The plant's described by a state model, equations 23 and 24. U of t is a deterministic input. Omega of t is an unknown random input called the plant noise. Mu of t is the random measurement noise, which has a corrupting influence on the sensor measurement. Which is denoted as measurement of t. The matrix C sub m is also known as the measurement matrix. The A matrix is known as the state transition matrix because it determines the current state x of t. We've been discussing state in terms of x, y, and z coordinates or position coordinates from the previous state x given t minus 1. I also want to mention that states can be things such as x, y, and z coordinates in the first moment, second moments, etc. So you can have x position, x velocity, y position, y velocity, and so on. Continuing the review, for random variable x at time t1 is independent of x of t of 2 for all t1 not equal to t2, then both the noises are white noise. If one random variable depends on another random variable at a specific time, and those times are obviously not equal, then the plant measurement noises are something called colored noise. Moving along, we'll discuss the correlation, covariance, and autocorrelation within a common filter construct. Correlation function depends on the time difference tau, as this cap r sub x for state x at time t1 and t2 is the expected value of a state x at times t1 times the transpose of that times t2 matrix notation, and then you'll see that's r sub x at tau. In other words, tau is the absolute value of t2 minus t1 or t1 minus t2, doesn't matter. It's an absolute value. A given x of t is expected value x of t, and expected value x of t is mu, which is m sub x, and we saw that in the previous slides, the measurement. It turns out that the state x at times t1 times its transpose, any matrix times its transpose is called a Gramian matrix, if you recall that. You presume that that's a symmetric matrix, and when you assume matrices are symmetrical, there's something called the spectral theorem, which says that we have a basis of eigenvectors and that every eigenvalue is real. Also, if A is a regular matrix, then A times its transpose is positive definite, so that's something to keep in mind when you're looking at the correlation function. Moving along, the time average of x at times t is denoted as that matrix we talked about, the A matrix times the state x at times t at the time autocorrelation of the state x of t, which we denoted as cap r at that state. Equations 26 and 27 define those in terms of continuous time, with equation 26 being the integral form of that. And again, tau is t2 minus t1, difference in times. An ergodic process is a stationary random process, and the A matrix times the state x times t equals the expected value of the state, and also that the autocorrelation function of the state parameter state and tau is equal to the autocorrelation function of the state at time tau. And again, E given the expected value of state at time t, can be called the expected value of the random variable x at times t. Question arises if the autocorrelation function x at times t and tau as its parameters, is that function linearly independent if the autocorrelation is 0? Yes, but obviously only if the state x times t equals tau. To review what linearly dependence means, a finite subset of n vectors, we'll call it vector v1 to vn, from a vector space V. Again, we use the state space S in some previous examples. Is linearly dependent if and only if there exists a set of n scalars, a sub 1 through a sub n, not all zeros, such that a1 v1 plus a2 v2 plus a3 v3 and so on equals 0. Autocorrelation is also equal to the expected value of a vector and its transpose if you assume linear independence, and that's a fallout of what we discussed on the previous slide. There's also a covariance function that depends on tau, denoted by equation 30, and again, tau is the absolute value of the difference in times, or the absolute value of the delta time. Correlation and covariance functions provide information on the correlation of random process variables over time. Excuse me. By looking strictly at the time period of strongest correlation, or the spread of these functions, you can define a correlation time per equation 30, and that matrix C sub x with the superscripts I comma I times tau. That I comma I is a component, the certain component of the covariance function. That correlation time is most frequently used for targets that maneuvering targets, but targets that maneuver radically, such as something like fighter aircraft. Next slide. The whiteness or color content of a stochastic process can be characterized by its power spectrum. Stationary random process frequency content is described by the power spectral density function, which has frequencies as parameter, and you can see integrating that over all frequencies is the signal's average power. Pretty well known equation. Equation 31. Power spectral density should be continuous, proportional to the power of the component sinusoidal signals with a certain frequency f sub x. Have its average defined as the average power we just discussed on the previous slide. Another definition of the power spectral density, it's the Fourier transform of the autocorrelation function. Autocorrelation function is in 32 for t is an element of the set with the range 0 to t, and t minus tau is an element of that same set, and then the autocorrelation is 0 elsewhere. So in other words, the Fourier transform of the autocorrelation function is defined by equation 32, and it doesn't exist if 32 is not true. So the linearly independent assumption for the autocorrelation function is confirmed by equation 33. Back to your Fourier transform basics. Fourier transform is signal denote cap x, evaluate over parameters alpha and beta from negative infinity to positive infinity, are defined according to equations 34 and 35. In that context, the power spectral density can be defined as the absolute value of x sub I given parameters cap t and f for frequency, and that absolute value squared. It's an integral of the autocorrelation function times an exponential j omega, where omega is 2 pi times the frequency times the time, over minus cap t to t, and that's all taken over a factor of 1 over t, and then again that's an integral sum. Again, I said omega is 2 pi times the frequency, and then there's a couple of assumptions on the average autocorrelation function. And I did want to mention the statistical distribution of noise in the power spectrum from a fast Fourier transform is a chi-squared distribution with 2 degrees of freedom. You'll see the chi-squared symbol in equations 34 and 35. The chi-squared, distribution is the sum of actual minus expected frequency squared over the expected frequency. That's the PDF for the chi-squared distribution. Linear system with a random initial state and a stationary white noise input can be modeled in continuous time according to equations 37 and 38. Omega of t is the white noise input function. In discrete time, any random sequence state vectors x sub k is uncorrelated by equation 39. I should note that the del of k minus a is a Kronecker delta function for k minus 1, as we discussed previously, k minus 1, t minus 1, whichever variable we want to use, that denotes the previous state. And 40 is the relationship between the power spectral density and the autocorrelation function. You'll recall that the expected value of omega times its transpose at time t and t plus tau respectively is equal to the expression on the right hand side for equation 40, and the expected value argument there is the Gramian matrix, as we discussed earlier. In a matrix application, that would be again a Gramian matrix. That's the expected value of that matrix. In practical terms for computing this, of course. Power spectral density represents the frequency content of a stationary zero mean random process. Mean of initial condition is assumed to be zero. The correlation matrix of the initial condition is assumed to be zero. From equations 25 and 32 previously, we have the mean. Its mean is, we could say this measurement of state x at 0. Mean of x equals 0, and autocorrelation function as we previously defined. Initial conditions are uncorrelated to input for all time t is greater than or equal to 0. Equation 43. We'll use white noise input for that. It can approximate a non-white color noise process input to a linear system. And a note says provides accurate result for large noise bandwidths, and is fairly a good representation of input under relatively small correlation times. The output spectral density of a stable linear system, you see in equation 44, and common filter nomenclature, G represents the plant transfer function. For non-white stationary random input, substitution of the frequency dependent input spectral density into 47 gives equation 45. These are approximately equal when the frequency dependent input spectral density is equal to the constant spectral density. That's a required equality. It holds over the range of frequencies where the absolute value of this plant function, G with an argument J omega, has elements that differ significantly from 0, and the takeaway from that is over the bandwidth of the system. Variance and correlation time characterize random inputs. It can be expressed into spectral density for an equivalent white noise input according to equations 46 and 47. If you take the Fourier transform, you get equation 48. At low frequencies, the spectral density is approximately constant. In other words, sine omega tau sub c, that's correlation time. Sine of the argument equals the argument. And you'll recall that's a specific assumption about the, I believe it's the small angle assumption or something to that effect, such that you get equation 49. Testing. Okay, back with common filter view of linear filter shaping. We're going to talk about noise autocorrelation, the Fourier transform, as we have been. Recall they have a state model given by equations 50 and 51. Omega sub t is an omega with an argument t is an unknown random input called the plant noise, and the measurement noise is mu given an argument of time in equation 51 that's the measurement equation. 50 is also called the state equation. I should have made that clarification earlier, or distinction. Suppose that omega with the argument of time is represented as a non-white correlated Gaussian noise, while mu at that same time can be represented as a zero mean white Gaussian noise. You can then model the unknown random input or the plant noise by linear shaping something called a linear shaping filter, which has the form in 52 and 53. If we accomplish a change in variable by letting a equals f at time t and b of omega equals g at time t, those f with an argument of time and g with an argument of time, both matrices, that makes the state transition matrix A and the plant noise covariance matrix B time dependence. Hence we get equation 54, and we can also take the omega with the argument of time, which he said this is non-white correlated Gaussian noise. We can take that and define that by equation 56, and we call equation 55 a linear shaping filter. Again, the has omega sub 2 at time t with a coefficient matrix of BSF denoting shaping filter. Same thing for A sub SF, the A matrix for shaping filter times state x at times t. The measurement M at time t is represented by the shaping filter omega 1 at times t. The plant noise is now represented by omega sub 2 at time t. We'll make another change of variable. This time it converts the state space model into a model for linear dynamic system in continuous time. We got then we get the general form of a first order differential equation in 57 for the shaping filter we've been discussed. You can take this first order differential equation and get equation 58 for the shaping filter. Let's see, I have a note that I've defined F for the shaping filter and G for the shaping filter and B for the shaping filter, as well as noise U at times t equals omega sub 2 at times t. And again, to clarify what the U is typically will be plant noise, and the measurement noise will be eta. Mu. Okay, we again make the change of variables to get equation 59 for a linear dynamic system in continuous time. We apply the shaping filter to get equation 60. Note the system state vector static in the sense of linear time invariant. I'm sure you're familiar with that term. A shaping filter and B shaping filter are now replaced by a time varying system state vector, which is dynamic, F of shaping filter and H of shaping filter at time t. Okay, state vector can then be augmented with the shaping filter states, such as the new augmented state vector can be constructed according to 61. We perform the change of variable we performed earlier. Develop equation 62, which is in the same form of equation 57. Now, disturbance input to the physical system or the plant is represented by the measurement omega 1 at times t of that h times x, h of t x at time t, where the C matrix at times t equals that H matrix at times t. The resulting linear shaping filter takes the form of equations 63 and 64. Basically, all of that is a fancy way of saying, um, looking at the block diagram on the next page, a shaping filter for non-white noise. You see the upper half of the block diagram is a shaping filter. The bottom part is a physical system. The entire two pieces, the augmented system, you feed omega sub 2 with time t into the shaping filter. Then you get an output that's in turn fed into the physical system or the plant. You see a feedback matrix F, and which is summed with the G matrix. There's an integration performed. You get the H matrix, and then you're going to get the output in terms of a measurement. For large correlation times, the disturbance input, or any random process specified only by the moments of mean and variance in terms of correlation time, can be modeled as the output of a first order shaping filter for the plant, given by cap G of S is B over S plus A in parens. Using an autocorrelation function for a Gauss-Markov process for exponential superscript minus AT, and taking the inverse Laplacian of that G of S function gives you B times the exponential. We're going to let alpha equal A, and alpha equals 1 over the correlation time, which we discussed previously. So obviously A equals the inverse of the correlate, or 1 over the correlation time, and we're going to define a second parameter B as 2 times alpha. Now taking the Fourier transform, you're going to get B times the exponential equals 2 alpha over alpha squared plus omega squared. The next thing we're going to do is incorporate the second order shaping filter into an equation we discussed previously. That's the time derivative of the shaping filter state vector is equal to F subscript shaping filter at a time times its state vector plus G, which is the plant coefficient for the shaping filter, times T times U of T. And of course, U of T represents noise on the plant. And then we end up getting second order shaping filter results, which you see defined as minus alpha times a state that defines a shaping filter, or a better way to say it's shaping filter state at a certain time, plus the noise omega sub 2 at a certain time. We take the piecewise solution. If you go back to your solution of linear differential equations, we're going to perform that calculation and get the piecewise solution as x at times k plus 1 equals that exponential times a shaping filter at time k, shaping filter state at times k, plus the same exponential at the noise omega sub 2 at the time k. You can manipulate that actually and put it in the form of the discrete Fourier transform synthesis equation. So again, this is a relationship between linear shaping filter for a common filter and the discrete Fourier transform. I'm not going to go into this in detail, but you have prediction and correction equations for the standard common filter, and you also have discrete time extended common filter equations for the same prediction and correction. You can construct a linearized common filter according to the table that you see in front of you, common filter equation, and then you have description of each of the parameters. Very briefly, you do have the covariance matrix. You initialize the state to 0 at time t, initialize the coefficient p, which is a covariance matrix that represents the relationship of the co-state to the state. You might use the term correlation coefficient is sometimes used. It's also the left-hand side of the Riccati equation. Then you update the state variable for the optimal feedback gain matrix, common gain K, and the measurement matrix mu. You get this optimal feedback gain matrix, which is the K times T is a common gain matrix. You have your steady state solution of the algebraic Riccati equation, and then you update your initial state with the optimal feedback gain, and all that gives you the linearized common filter. Nonlinear plant measurement models can be done with both the continuous and discrete time. You have plant and the measurement, and the noise for the plant and the measurement, respectively. We've discussed some of this, but not all of it, so I'm not going to go into that in detail. Just note that those are computations that can be performed when the plant and the measurement are in the model nonlinear stochastic process. Moving on, we're going to discuss the substance of this project report, which is using the common filter, extended common filter, and Bayesian multiple hypothesis tracker and a surface search radar target tracking problem. This paper is going to illustrate the hybrid approach to the nonlinear multiple hypothesis tracker problem. What I've done is demonstrate a single target can be tracked in multiple dimensions in cases where the standard linear Gaussian assumptions don't hold. I note in that case the extended common filter can be used. Also use some elements of feature extraction. It's based on a hybrid algorithm that uses a standard common filter for track prediction when the rank of the measurement matrix is insufficient for Bayesian multiple hypothesis tracking. In this algorithm, a standard common filter is used for the prediction step, a single hypothesis tracker, or an extended common filter is used for the correction step, if you remember the prediction and correction step slides that I went over just very briefly. Modeling a surface search radar system in this manner, you're going to assume the track measurements are taken from a GPS constellation which provides 3 parameters: latitude, longitude, and altitude. What I did is a series of coordinate transforms from Earth-centered latitude, longitude, altitude to Earth-centered, Earth fixed, then to northeast down in principal component directions X, Y, and Z. And then implement an extended common filter and convert the coordinates back to latitude, longitude, and altitude for display. Now, if the altitude measurements didn't exist or were not sufficient, or you have erroneous or corrupted data, the correction step wasn't performed. In that case, i.e. the loss of altitude from a GPS signal, you can use a standard common filter instead. The criterion for using a Bayesian multiple hypothesis tracker is the rank of the measurement matrix. If the rank is less than or equal to a threshold tau, the extended common filter is sufficient and can be used for your correction. That's single hypothesis tracking, which I did model and I'm going to illustrate shortly. If the rank exceeds the threshold, and I believe the threshold I determined for the scenario that I modeled is 3, then the multiple hypothesis tracker should be used for the correction step. The reason you want to use a multiple hypothesis tracker, it more accurately models the distribution of real error in the estimated positions by means of Gaussian mixtures rather than a single Gaussian. Again, I didn't model this, but if this threshold um, rank of the measurement matrix was greater than what I found, which was 3, then you would use the Bayesian hypothesis tracking. Basically, you would look at additional data added to your state vector, additional information, and then it might be possible to model it more accurately with the Bayesian MHT approach, which again wasn't done by the example I'm going to demonstrate. I have a bullet for the EKF case model. The rank of the measurement matrix, also known as H, typically in common filter nomenclature, was 3. For the standard common filter case, the rank of the measurement matrix was 2. You might notice that the rank equals the number of dimensions. So latitude and longitude would be measurement matrix 2, latitude, longitude, and altitude, measurement matrix 3. If you had another measurement, position measurement you wanted to put in there, or if you could somehow maybe put velocity or another factor in there, and you had a case where you had a rank higher than that, it's basically it's related to the curse of dimensionality. Someone worked out a nice way to handle that. It's very computationally intensive, but it can be done. For cases where the measurement matrix rank tau equals 3, the common filter is sufficient to model the problem described. So, in other words, my model is sufficient for the scenario in which that I chose using extended common filter for surface search radar, because it doesn't exceed the tau threshold, and I don't need to use a Bayesian multiple hypothesis tracker. The slide, this is entitled Common Filter Predictor Corrector Block Diagram. It's also called the observer form of the extended common filter. I thought it might be useful to see this because we've been talking about prediction, correction, which type of filter to use for a predictor and which type of filter to use for the correction based on the requirements of the tracking system, the radar, whichever sensor you're trying to model. I should note the extended common filter predictor corrector form is used since the derivative of the state is predicted from old data and then corrected using current data. So the extended common filter can perform a prediction and then a correction. I have a MATLAB model, a surface radar EKF 3D. It's a MATLAB M file. What that does, it initializes the observer and target latitude, longitude, altitude, course, and speed. The observer altitude is 10,000 feet. The target's altitude is 2,000 feet. This would be similar to using a surface search radar to track a low-flying aircraft. Of course, it could track surface ships, but this is just the scenario I chose. It initializes or zeroizes, or zeros, the state vector, the target range, bearing, and altitude, defines a covariance matrix P, which we've discussed. It's setting the covariance matrix update to U. So those are conventions. Covariance matrix being P, and the covariance matrix update is U, in extended common filter nomenclature. The measurement matrix is initialized. And the measurement matrix is, we denote that as H, which I've mentioned previously. That's a Jacobian matrix of partial derivatives, again, typically denoted by H. The time interval for this simulation is 1 second or 1/3600th of an hour. The target's initial velocity, the north component only, is defined to be 150 knots. What this model does is obtain sensor measurements, perform the coordinate system transforms I discussed before to calculate the relative distance in northeast down coordinates, converts these relative distances back to Earth-centered Earth-fixed coordinates, and then converts them back into a deltitude, latitude, and longitude, and altitude. So it's a relative position difference between the sensor and the target the sensor is measuring or looking to establish a track on. The model converts the target's course speed and latitude to north and east velocity components in knots. The plot you're looking at now is what this surface search radar does with 3D target true track and measurement data. What you can see with the empty red circles are the measurements that were made by the sensor. Based on those measurements, truth track was developed, which is the blue line. You'll see they're actually a series of dots, and the teal points show what the common filter, extended common filter, predicted as a path. You also see this plotted the north velocity, east velocity, and speed. One thing to note about this real quickly is that the green trace for east velocity is pretty high in magnitude. I'll make sure if I'm looking at the axes right. The east velocity, while the north velocity component actually doesn't make up as much of the plot. And of course, the north velocity squared plus the east velocity squared, take the square root of the sum of squares, and you'll get the speed vector, or you can use the root mean squared. But typically velocities and components